Hey there! Today, we're exploring a crucial component in our electrical and electronic system, the diodes. You can find them in your phone charger, TV remote, and those bright LED lights in your room. But what's a diode, and why should you care? Well, a diode is a special electronic component that allows electric current to move easily in one direction, but resisting it in the other. If you enjoy the content, please don't forget to hit the like button, subscribe to the channel, and turn on the notification bell so you never miss any update. The core of diodes is made of semiconductor, a special type of material from group 4 of the periodic table, such as silicon. They have 4 valence electrons in their outermost shell, often called the valence shell or valence band. But here's the thing, these atoms prefer to have 8 electrons in the valence shell to feel complete. To reach this stable configuration, silicon atoms come together and share their electrons, creating a crystal lattice structure. Now, through a process we fondly call doping, we can transform the semiconductor into either a p-type or n-type by introducing some impurities. For n-type, we introduce a few atoms from group 5 of the periodic table, like phosphorus or arsenic, into the crystal lattice. These atoms have 5 valence electrons, and bring an extra electron that doesn't have a pair to bond with. These extra electrons become free electrons in the crystal, which means they can move around and participate in electrical conduction. On the other hand, for p-type, we introduce some atoms from group 3, such as boron or aluminum. These atoms have only 3 valence electrons to bond with neighboring atoms, leaving some holes in the lattice. In a diode, we bring these p-type and n-type semiconductors together, creating a special border known as the p-n junction. Now, this is where things get interesting. At this junction, the free electrons from the n-type region start moving toward the holes in the p-type region naturally. The recombination of electrons and holes creates a layer of positively charged ions on the n-type region and negatively charged ions on the p-type region. This creates a zone called the depletion region. An electric field forms, setting up a barrier of potential energy that stops the flow of electric charge across this region. That's it, a diode is formed. Moreover, the end near the p-type is called the anode, and the other end near the n-type is called the cathode. Moving on, we can understand how a typical diode works by looking at its current voltage characteristic graph, or can be known as IV curve. It's a graph that shows how much current flows through the diode as we change the voltage applied to it. The IV curve can be divided into 3 distinct regions: forward bias, reverse bias, and breakdown region. Let's explore each of these regions one by one. When we connect a voltage source's positive terminal to the anode, and the negative terminal to the cathode, the diode goes into forward bias mode. Now, as we gradually increase the voltage, the depletion region becomes thinner. When the voltage reaches a certain level, known as the diode's forward voltage, usually around 0.6 to 0.7 volts for silicon diodes, the diode completely overcomes the potential energy barrier at the depletion region and becomes a good conductor. This allows a substantial flow of current through it. However, it's essential to remember that the output voltage will be slightly lower. For instance, if the diode's forward voltage is 0.7 volts, and we supply a 5-volt voltage, the output voltage to load will drop to 4.3 volts. Conversely, when we reverse the terminals of voltage source, the diode enters reverse bias mode. In this setup, the free electrons in the n-type region are drawn toward the positive terminal, while the holes in the p-type region are drawn toward the negative terminal. This action causes the depletion region to expand, and it becomes challenging for electrons from the n-type region to reach the holes in the p-type region. This effectively blocks the flow of current in reverse direction. Only a tiny leakage current, often in the order of microamperes, can pass through the diode in reverse bias mode. This behavior is useful in various electronic applications where we need to prevent current from going the wrong way. However, it's important to be cautious when connecting a diode in reverse bias mode. Going beyond the diode's peak inverse voltage limit can lead to a breakdown. In this breakdown region, the current suddenly surges and can potentially damage the diode. Furthermore, diodes have a remarkable characteristic, in which they can be designed to either absorb or emit energy, specifically electromagnetic waves at certain frequency. To understand this, let's look at the structure of an atom. Valence electrons require an energy boost to transition from the valence band to the conduction band, where they become free electrons, capable of conducting electricity. Conversely, free electrons in the conduction band possess excess energy, and they release this energy when they fall back into the valence band. This energy difference is termed the band gap energy. Now, when a diode conducts current, the free electrons from the N-type region fill the holes in the P-type region and emit energy equivalent to the band gap energy. Up until now, we've learned that diode operates based on IV curve and can emit energy or electromagnetic waves while conducting current. But how do we customize diode to exhibit unique IV curve or emit electromagnetic waves at a specific wavelength? The key lies in the precise adjustments to the type of semiconductor employed, the impurities introduced, and the doping concentrations. These variations can influence the thickness of the depletion region and band gap energy levels. As a result, we end up with a variety of diodes, each characterized by a unique IV curve and wavelength. These distinct diodes can be used in various fields and scenarios. One of the common and essential applications of diodes is the conversion of AC waveforms into DC. AC current flows back and forth in both directions. But as we mentioned earlier, diodes are smartly designed to be in forward bias during the first half cycle, allowing current to pass through while blocking the second half cycle in reverse bias. As a result, the output becomes unidirectional. To achieve a more consistent DC output, a capacitor is often introduced into the circuit for smoothing. Another important application of diodes is in voltage regulator circuits. Voltage regulators are essential for maintaining a lower, but consistent output voltage level, even when there are minor fluctuations in the input voltage. Zener diodes are specifically designed for this purpose. Zener diodes work effectively in the breakdown region, characterized by a well-defined breakdown voltage, known as the Zener voltage, or VZ. By connecting a Zener diode in reverse bias mode, and parallel with a load, you create a path for current to flow through the diode in the reverse bias mode. As the input voltage surpasses the Zener voltage, the diode will undergo Zener breakdown, and efficiently conducts just the right amount of current to maintain its voltage level at VZ. This feature is essential for ensuring a consistent output and the stable operation of the connected load. Moreover, diodes can be designed to receive and emit specific energy or electromagnetic waves, as mentioned earlier in this video. One example is infrared diodes, commonly used together with infrared receivers for remote control applications such as operating air conditioning units, televisions, or radios. However, we might not perceive the emission of infrared light because it falls outside the range of wavelengths that are visible to the human eye. In contrast, light-emitting diodes, or LEDs, are specifically designed to emit visible light in a range of colors. This includes the familiar red, green, and blue LEDs. When we combine these three colors, it can result in white LEDs commonly used in many lighting applications. Diodes serve many other functions as well, including radio demodulation, reverse current protection, photodetection, overvoltage protection, and numerous others. Although you can explore these various applications in more detail, it's crucial to keep in mind that the fundamental operating principle of diodes remains the same across different use cases. That's it for today's video. I hope you have a clearer understanding of diodes. If you find this video helpful, please remember to like, subscribe, turn on the notification bells, and share it with others. Thank you.